So today we're going to be talking about rational expressions and fractions, and we have to talk about a little bit. We have to talk about what those words actually mean. So rational expressions is a fancy term for something that can be divided by something else. The word rational comes from ratio. So if you think about a ratio, you have something, we'll call it P, that you're comparing to another thing, Q. You want to know how many of P do you have divided by Q. For example, if I have 3 apples and I have 2 oranges, the ratio of apples to oranges is 3 oranges to 2 apples. Okay? So we talk about these ideas when you're in elementary school or you're in 1st and 2nd grade and you're learning how to multiply, you're learning how to add and subtract. We like to start off with actual objects, right? Because it's easy to conceive of these things as, oh, I have 3 of these objects that are oranges and I have 2 of these objects that are apples. But when we get rid of these objects and we just call it 3 over 2, now we have a fraction, right? We have the idea of a fraction. Well, what does the word fraction mean? Where does that word come from? Well, it comes from the word, the Latin word, fracture, which if you've ever played any sports, you know is a break. You've broken something. And that's usually what happens to your brain when you get to fractions, right? Your brain breaks. So what we're going to do is we're going to make your brain get back together, okay? That's what we're going to do. And hopefully we're going to do that by talking about what fractions actually represent. They always represent ratios. They always represent comparisons of one thing to the other. Now, the question that I want to ask is, why is this comparison valuable? Why do we use these things? And where did this idea come from? Well, to do that, we can talk about the origin of mathematics and spend a whole lot of time. So I'll try not to do that. I'll try to just talk about how we get from whole groups of oranges and apples to just fractions of things. Well, think about the people who would have more than one orange or more than one apple. You know, think about people who would have hundreds of apples or oranges or hundreds of sheep and goats. These are people who are the business people in society. So this is where these ideas come from. They come from people, they come from civilization, from agricultural civilizations, the first of which was the Babylonian Empire. And we had these guys who collected and grew things and harvested things, and they needed to know how much they had. So this was a significant shift in the way that we thought about groups of things. For example, there are tribes even to this day, one of which is the Veda tribe in Sri Lanka. And if you asked a Veda tribesman who was gathering sticks how many sticks he had in his pile, he could tell you while he was putting the pile together that he had 1 stick, and then he would pick up the next stick and say, oh, I've got another stick. But then you point to the pile and you say, well, how many sticks do you have? He would look at the pile and go, oh, that many. Because they don't have a word that specifies quantity. It requires that we have symbols for quantities instead of the idea of a quantity. In our language, in English, we have words for groups of things, like how many cows are in a herd. We have a word for cows. It's called a herd. We have a word for a group of birds called a flock. We have these ideas for groups, but where we're different is that we've adopted a way of thinking about how to quantify these groups. And that's what these rational expressions and fractions actually represent, is how to quantify these kind of things. So when you're working with these fractions in your classroom, try to recall where they came from. They came from these ideas of comparisons of things and then the very necessary need to quantify them, not just to put them in a group, but actually put a value to that group.
There are going to be some occasions where we are going to be either adding, subtracting, multiplying, or dividing fractions of this nature. And in that case, we're going to, let's see. Okay, so let's say we are given two fractions. 1/2 plus 1/2. Well, if we represent this as a picture, each fraction, the bottom number, is telling us how many parts of the whole we have. So in this case, we have 2 parts of a whole object. The number on top is telling us how many we're actually looking at. So in this case, only 1/2. Okay? So if we have 2 fractions and we want to add or subtract them, well, it's easier if we're talking about the same number of parts in this whole. And another way to say this is they need to have the same denominator. The first case is if the denominators are the same, in which case we can see that 1/2 plus 1/2 will give us the whole object. To do this with the fractions, you keep the number of parts of the whole on the bottom, the 2. And then we are going to add the 2 parts we're talking about in the numerator. In which case we get 2/2, which represents 1. Okay? So another situation we want to look at is if we're adding 2 fractions that represent different parts of a whole. So where the denominator represents how many parts the whole object has, and the numerator represents how many pieces we have of that whole object. Okay? So in this case, we have an object that's broken into different parts. One is broken into 2 parts, and one is broken into 4 parts. But we want to add these 2 quantities together. So in order to do that, we want to cut our holes into the same number of pieces. So when we're doing that, the first thing we should look for is if one denominator is a multiple of the other. So for example, if I multiply this 2 by another 2, I can get 4 here. So if I want to do that, I'm only going to multiply this fraction by 2 there. Now whatever I do to the bottom, I'm going to have to do to the top in order to keep this ratio the same, or equivalent. So now our new expression, this first fraction, is going to be 2/4. And now we can add the 1/4. Now that they're broken into the same number of pieces, it's easier to compare how many total we will have. So now we have 2 of the 4 pieces from this and 1 of the 4 pieces from our second fraction. So we can see, adding straight across, the numerator always stays the same because we're going to have the same number of parts in this fraction. But because we've combined these 2 parts with this 1, or we've added 2 plus 1, we now have 3/4 of this whole.
You said numerator.
Numerator's top, denominator is on the bottom. So the numerator is how many pieces we are talking about. The denominator is how many pieces are in the whole object. So the other case where the denominators are different is when one is not a multiple of the other. So for example, if we're adding a third and a fourth. Well, a third of if we break an object into thirds, it looks something like that in this case. An object into fourths would be like that. It's kind of difficult to compare that way. So we're going to want to break these into the same number of parts. So in order to do that, we need the least common multiple. Now one way to do that is we can look at all the multiples of 3. We have 1 times 3, 2 times 3, 3 times 3, 4 times 3. This would give us 3, 6, 9, and 12. And we can do the same thing with the other denominator. We'll look at the multiples of that denominator. 2 times 4, 3 times 4. This gives us 4, 8, and 12. Now what this tells us is they both can be broken into 12 pieces. There and there. So that's the number we're going to go for. Now, in order to represent this as 12 pieces, we're going to need to multiply 3 by 4 in order to get that number. And if we multiply the bottom, we also have to multiply the top. In this case, in order to get 12 on the bottom, we're going to need to multiply this 4 by 3. And again, whatever we do to the bottom, we have to do to the top. So our two new fractions are going to be 4 over 12 and 3 over 12. Now that we're talking about the same number of pieces, we can just add the tops together, the numerators. 4 plus 3 over 12. And we find that we have 7 of the 12 parts. Okay, so the next thing we're going to talk about is subtracting. And essentially, subtracting has the same rules, where if we have 2/3 minus 1/4, again, we're going to want to break these into the same number of pieces. So we're going to want to find that common denominator. Like the last example, we already found that 3 and 4 can both go into 12. So we can break both of these fractions into 12 pieces. So we'll multiply this denominator by 4, as well as the top. And we'll multiply this denominator by 3, as well as the top. And our new fractions will be 8 over 12 minus 3 over 12. Now, the same rules apply for subtraction that they do for addition, where the denominator will stay the same because we're still talking about the same number of parts. But now we're taking these 8 parts that we had and we're subtracting 3 of them away, leaving us with 5 of these 12 parts. So for addition and subtraction, it's important that before you do anything with the numerators, these denominators have to be the same. Okay. All right. So then the last thing I need to talk about is multiplication and division. So multiplying fractions is probably the easiest operation you can do with the fractions because they don't have to have the same denominator. If we have 1/4 and 1/3 again, well, with multiplying, you can just multiply the numerators together and the denominators together straight across. So this would be the same as 1 times 1 over 4 times 3, which would give us 1 over 12. Again, you do not need a common denominator for this part. And with division, so if we have 1/4 divided by 1/3, we're essentially going to turn this into a multiplication problem by doing skip, flip, and multiply. So what I mean by that is we're going to skip this first term and leave it exactly the way it is. We are going to flip the second term. So the denominator is now the numerator, and the numerator is now the denominator. And instead of dividing, we're now going to multiply. So it's the same process as it was up here, where we're just going to go straight across. You multiply your numerators, you multiply your denominators, and you get an answer. So the question was, why, when we multiply two fractions together, do we get a smaller fraction? Well, in order to do that, we have to think about what these mean. So if we have an object, and let's say we're breaking this side into the 4 pieces, and this side we're breaking into 3 pieces. So this would represent our 1/4 and our 1/3. Here's a 1/3 segment, here's a 1/4 segment. So each of these 1/4 will add up to give us our whole. Now, when we're saying we're multiplying these, we're saying we have this 1/4 of a segment 1/3 of a time. Now, when we think about this is where the common denominator comes in, because now we're talking about the same number of pieces, where this object is going to be broken up into a total of 12 pieces. And of those 12, we have just the one.
So picking up where we left off with the adding of fractions, let's go ahead and use a method to do this with. I like to call this fractions are our friends, but you'll notice that it's actually just a butterfly. So it makes it fun and pretty and easy to organize. So welcome. So we're going to start with an example of 3/4 plus 5/10. All right, so like was said before, we need to have a common denominator. And while we can easily do 4 times 10, we're going to show a way that we can organize this method. So the first thing that we're going to do is we're going to draw one wing of the butterfly, and I'm going to do this in green. I'm going to draw the second wing, or the second part of the wings of a butterfly, and I'll do this one in blue. And then every butterfly has antlers, so we'll put them up, or antennae, not antlers. And then they all have a little cute butt, so we're going to draw that in. Okay, so with this method, it's a way to organize exactly what you're doing when we add fractions. So we need that common denominator like we had said. So we're going to go ahead and do this 4 times 10, but we're going to put that number in his cute little bottom. So we'll have 4 times 10, and that's going to be then 40. Now that we have our colors the way they are, it's easy to see how they group. And we're going to still just work with multiplication. So we're going to have the 4 times the 5, and we're going to go ahead and put him under the antenna. So we'll have 4 times 5, and that's going to be 20. And we'll do the same thing with the blues that we've circled. So 3 times 10 is 30. And now we have all of the parts we need to actually add this fraction together. So we just put them in their correct pieces. We have 40 on the bottom, and I called it a cute bottom, so it's easy to associate with. And we have the 30 on the top. We have a 20 on the top. And you can do this for subtraction as well. You just notice what the operation tells us to do, and that would be the sign that you put in between. So this one's addition, and we'll go ahead and add it. And then we just do what it says. So 30 plus 20 is 50. We have that over 40. The biggest part with this method, the biggest rule with this method, is simplify your answer at the end. While this is a correct answer, it's not necessarily in its simplest form. So we're going to go ahead and reduce that into its simplest form. I like zeros because to me, you just know you can knock them off. You don't have to think as much. I'll do it this way so you can see it. And we end up with 5/4. So this method works for adding and subtracting any fraction that you have or any rational expression that you have. While I did this with numbers, we can actually put letters on it instead, or variables as well. So I'm just going to do a real quick modification, and then we'll let you guys have an activity. So let's say we start with 3x, and we start with 10x on the bottom here. All it will change is what our answer is in these sections. Actually, I erased that one, and I didn't need to. 4 times 5 is still 20, so we'll keep him there. That looks like a minus. Perfect. And now we have our 3x times a 10x, which will be, ooh, I'm doing it in red, 30, and x times x is x squared. And again, remember how I said that now we have all the pieces, and we just combine them over there. The bottom is still the bottom, but we need the x, correct? Because we added an x on the bottom. So it's 4 times 10x. We get 40x. Our new cute little bottom is 40x. We'll have our 30x squared plus our 20. In this case, we can see if that's its simpler form. Remember I said at the very end we need to make sure we simplify. So then we just need to see, is this its simplest form? Some teachers will let you leave it like this. Other teachers want you to simplify it completely altogether. Mathematically, this is absolutely correct, but let's go ahead and simplify it some as well. There isn't anything or a greatest common factor on the bottom, so the bottom is going to stay 40x. And our top portion, there's a common factor of 10 in both of those. So we'll go ahead and take that, factor that 10 out, and we'd be left with 3x squared plus 2.